So we're going to learn how to write Lewis structures for covalent compounds, things like water and ammonia and ethane and different things like that. So here are the steps. We'll go through the rules, the instructions, and then we'll do some examples, and hopefully it'll become a little clearer. So first we write the correct skeletal structure. That is, how do the atoms connect to each other? So some guidelines, because this can be sort of an iffy guessing game. The hydrogen atoms are always terminal, meaning they're on the ends. Hydrogen has one electron to share. It always makes one bond. So it can't be in the center of a molecule where it would have to form two or more bonds. It's just too small. It can't do that. So hydrogen's always on the outside of our structure. Another thing to keep in mind is that many molecules tend to be symmetrical. And so if you can arrange them in a way, where you've got the odd one in the middle and the ones that you maybe have 4 oxygens and put those around, that's typically how it's going to go. You'll find that some of the homework or worksheet problems may be challenging in terms of knowing how to connect things. On exams, where the points are important, I will try to be very clear. Either there's really only one possibility, or I'll tell you this is the central atom to give you a start on how to put it together. The next thing is to figure out how many valence electrons are there in the whole structure. So you look at each of the atoms in your molecule, you find it on the periodic table, you determine how many valence electrons it has, and you add those all together. Those are the number of dots that you have to mess around with. For ions, you will have to either add or subtract electrons. That's how ions are formed. If you have a negative ion, that means you have extra electrons. We're not going to worry about where they came from. We just got extra ones. If you have a positive ion, that means it's short electrons and you have to take one or more away. Next, you take that number of electrons that you've determined you have to work with, and you distribute them around to the different atoms, and you try to get everybody to have an octet, duets for hydrogen. Start by putting 2 electrons between each pair. You have to have at least a single bond connecting the atoms, so that'll be 2 electrons right there. And then put the remaining electrons around the outside. Sometimes you run out of electrons before you've given everybody an octet. That means that more sharing is needed, and so you're going to make double or triple bonds. So let's do some examples. Write the Lewis structure for carbon monoxide. So the first step is to figure out how do those connect? Well, this shouldn't be too tough because there's only 2 atoms. They must be connected to each other, right? So here's carbon and here's oxygen. They're going to be next to each other. Next, we need to figure out how many valence electrons do we have to work with. Carbon is in group 4, and so it has 4 valence electrons. Oxygen is in group 6. It has 6 valence electrons. We add those 2 together. We have 10 valence electrons. So we have to have a bond between these 2. So there's my bond. That's 2 electrons. If you have a hard time remembering that that's 2 electrons, go ahead and put dots on each end. So I put in 2 electrons. I have to bond everything together. And then I'll put the others as pairs around. So there's 2 electrons. 4, 6, 8, 10. There's no one perfect way to do this. There's multiple ways to get a correct result. Does everybody have an octet? So how do we count that? Here's carbon, 2, 4, 6. Nope, oxygen, 2, 4, 6. Nobody has an octet. And so you can mess around with this and see what you can do. I could move those over here. Now, carbon has an octet, but oxygen doesn't. There is no way to have octets for everybody with just a single bond. What we need to do is do more sharing. So I'm going to take one of these lone pairs, and I'm going to make it a shared bonding pair in between. So I'm just going to take this guy over here. So I'm going to take those off, and I'm going to put them in here and connect them. That's a shared pair. I still have the same number of dots. 2, 4, oops, I didn't mean to do that. 2, 4, 6, 8, 10. I haven't changed the number of electrons. I'm just moving them around. Now when I look at this carbon, I've got 2, 4, 6, 8. This carbon has an octet. The oxygen has 2, 4, 6. We're still not good enough. I need to take another lone pair and make it a bonding pair. So if I take this lone pair and stick it in here, that's going to give carbon too many electrons. And I could fix that by taking this lone pair and moving it over here. Or I could, think ahead a little bit and say, well, this one already has an octet. So we'll have carbon share more with oxygen. So I'm going to move one of carbon's pairs to be a shared pair between them. So I've got 3 bonding pairs. So carbon counts 2, 4, 6, 8. Oxygen counts 2, 4, 6, 8. It's kind of awkward and ugly, right? So your first structure is going to be a little messy, then rewrite it neatly. So over here, I'm just going to rewrite that. I'm having a triple bond. So 3 lines. And personally, I like things to be symmetrical if I can make them that way. So I'm going to put the lone pairs on the outside. It doesn't matter if you put them on the top, the bottom, it doesn't matter, but there they are. So carbon has 2, 4, 6, 8. Oxygen has 2, 4, 6, 8. Any questions?
What was the charge on that?
0. The charge is 0. This is a molecule. There's no charge written on it. And so overall the charge is 0. You can do this for polyatomic ions, but the charge will be written. Unfortunately, on exams and the worksheets and stuff, those minus signs are really small. Let's do another one. H2CO. Well, now we have to figure out how are we going to stick these together. We've got 2 hydrogens, a carbon, and an oxygen. The hydrogens can't be in the middle. Many of the molecules that we're going to make have a central atom, one that's in the middle, and the others are kind of arranged around it. Oftentimes, how the formula is written should suggest what you might try to do. So the fact that C is in the middle of this is a good indication that we should try putting carbon in the middle and connecting the other things to it. So put a hydrogen here, perhaps, and a hydrogen up there, and an oxygen over here. And then we need to count up valence electrons. Hydrogen has 2 valence electrons, and 1 valence electron. Hydrogen has 1 valence electron, there's 2 hydrogens. Carbon, how many valence electrons? What group is carbon in? It's in group 4, has 4 valence electrons. How many valence electrons does oxygen have? 6. I write O. Good grief. So the number of valence electrons is just the group number. 1A, 2A, 3A, 4A, those group numbers. Okay? So this is giving me 12. I've got 12 dots to mess around with. I need bonds between all my atoms. So, probably drew these too close together. So, I'm making those bonds. So I've used up 2, 4, 6 electrons, and the rest of the electrons I'm going to start throwing around as lone pairs. So 2, 4, 6, 8, 10, 12. I don't want to give any lone pairs to hydrogen. Too small, can't handle it. Hydrogen is happy with the one bond, easily satisfied. So then we assess, is everybody happy? Well, this carbon has an octet, 2, 4, 6, 8. This oxygen has 2, 4, 6. Not happy. We need to share more. We need to make a double bond. So I'm going to take a lone pair from the carbon because it has 8 and I don't want to give it any more. So carbon is going to take this pair of electrons and share with the oxygen. Now the carbon has 2, 4, 6, 8. The oxygen has 2, 4, 6, 8. Each hydrogen is happy just with a single bond. Everybody's good. Let's draw this a little neater. So carbon, a single bond to a hydrogen, single bond to the other hydrogen, a double bond to the oxygen, and then put in the lone pairs. Oxygen has 2 lone pairs. Any questions? What about polyatomic ions? Same idea, same process of writing this structure. Pay attention to the charge though. Every negative charge you have to add an electron, every positive charge you have to subtract an electron. When we're doing charged things, ions with Lewis structures, we're going to put brackets around the Lewis structure and put the charge on the outside, unless you're doing mastering chemistry. Okay, let's look at cyanide. Oops. So the cyanide ion. So here we have a polyatomic ion. It's got 2 different elements and it's got a charge on it. So we're going to have, that was really big carbon. We're going to have carbon and we're going to have a nitrogen. Next step, count up electrons. How many valence electrons does carbon have? 4. How many does nitrogen have? 5. What do we do with the -1 charge? We want to subtract because it's negative. We need to add an electron. We are adding an extra negative charge. So we're going to get a total of 10 electrons.
Where's that electron coming from?
Where does the electron come from? It would have come from most likely some metal that it interacted with. Just like when we made sodium bromide, bromine became an ion by gaining an electron. Where did the electron come from? It came from the sodium atom. So when we're doing these structures, we are looking at the ion after it has formed. That electron had to come from somewhere, had to come from an atom, but we don't know because we're not looking at the chemical reaction. Does that help? Sort of? It's kind of an iffy answer, yeah.
So is the Lewis structure just getting the electrons from both and then the charge or subtracting the electrons?
Say that again?
So the electrons, 4 came from the C,
Right.
and 5 came from the N,
Yeah.
and then 1 came from the negative.
Right. So when we're adding up these charges, the carbon has 4 valence electrons, the nitrogen has 5 valence electrons, and the negative charge tells me that as a unit, this has 1 extra electron. That came from somewhere, but we don't have any information here about where it came from. It had to have come from an atom at some point. Where it came from now is not that important. It belongs to the cyanide. Somewhere there's a positive ion who's short an electron. So we have 10 electrons. We're going to start with a bond between these two. Got to have single bonds to connect things, otherwise they're not connected. So there's 2 electrons, and then we're going to put lone pairs around. 2, 4, 6, 8, 10. I ran out of electrons. Nobody has an octet. I'm out of electrons. That means we need to make multiple bonds. We need to share more. So I'm going to pick one of these lone pairs and stick it in the middle. So I'm going to erase it and move it. I'm going to put it in here, and that's now a bond because it's shared. A pair of electrons that are shared. This carbon has 2, 4, 6 electrons. The nitrogen has 2, 4, 6, 8. Now we've got an octet on one, but not the other. We don't stop until everybody's happy. So I'm going to take a lone pair from the nitrogen because it has the octet now, and I'm going to share that with the carbon that doesn't have the octet. So I'm going to steal one of these and move it over here and connect the dots. That's now a shared pair. It's a bond. Carbon has 2, 4, 6, 8. Nitrogen has 2, 4, 6, 8. This has a charge. So we should put brackets around it and write the charge outside the brackets. It's kind of an ugly Lewis structure, so you might want to rewrite that. Normally we write the bonds as just lines. The nitrogen, and then each of these has a lone pair on it, and overall this has a negative charge. Any questions? Pardon me? No tensile bonds? No central atom. Is that what you're asking? I'm sorry, I'm not quite understanding.
So I said, is there's only triple bonding? There's no tensile bonding?
Oh,
You still have
4 bonds.
2 pairs.
Yeah, you can't have 4.
Okay.
Yeah. For this class, 3 is the maximum. You hear me say for this class a lot because we lie to you. It's for your own good, right? We lie to you. Any other questions? Okay, let's do this one. This is the hypochlorite ion. Okay, there's a negative charge here. You could also draw a Lewis structure for a ClO molecule, so you have to pay attention to those charges or lack thereof. So again, we've got 2 elements, so they're going to be connected to each other. Then we have to add up numbers of electrons. How many valence electrons does a chlorine atom have? 7 valence electrons. It's in group 7. And how about oxygen? 6. What do we do with the negative charge? We add 1. So this ion is going to have 14 valence electrons in its Lewis structure. So we have to have 1 pair that's shared, otherwise it won't be a unit. So there's 2 electrons, and then 4, 6, 8, 10, 12, 14. Hey, we had enough that time. Awesome. Brackets and a charge. Normally you would see this bond as just a single line. And kind of make it that way by just making it fatter. But remember that each line is 2 electrons.
So if they're not the same number of electrons on both sides, that's when you have to put them in the middle?
It's not really that we're trying to balance the number of electrons on each side. It's that we're trying to have everybody have 8. 8's the magic number. Any other questions?
Why don't you make 3 bonds?
Why don't I make 3 bonds? That's a good question. If I made 3 bonds,
It's more strong.
right, it would be stronger. So if I made 3 bonds, so there's 2, 4, 6 electrons, 8, 10, 12, 14. Why not? Well, how many electrons does chlorine have now? 2, 4, 6, 8, 10. It's too many. 2, 4, 6, 8, 10. So that's not an octet. It's too many electrons. Did I do that right? 2, 4, 6, 8, 10, 12, 14. Yeah. So we're not going to do that because that would give us too many. We're not, you know, sometimes more is not better. We're going for 8. There are molecules that do more than 8, but we don't want to talk about them. So we're just going to share enough that everybody gets 8 except for hydrogen who gets 2. So here's the exceptions. We're going to mention them. Sometimes it's impossible because to write a good Lewis structure that follows the rules because there's an odd number of electrons. So if we look at my favorite molecule, no. Nitrogen has 5 valence electrons, oxygen has 6. No matter how you add that up, it's an odd number. And you can mess around moving those dots around all day long. You cannot give both of them 8. So this is a molecule that violates the octet rule. You just draw the best you can and leave it at that. There are other exceptions for some of these smaller atoms like boron. Boron is sometimes happy with 6. So boron trihydride, boron trifluoride, they're going to do that. I want you to be aware of them. That's pretty much it. If you take Chem 1A, we'll talk more about them and understand how to predict when that happens and when it doesn't happen. So those are 2 exceptions. Another exception is an expanded octet. Things like sulfur hexafluoride, phosphorus pentafluoride, they can actually have more than 8 electrons. These are called expanded octets. This only happens with the larger elements. It does not happen with the period 2 elements ever. Period 3 elements do this sometimes. We're not going to worry about it except just to understand that it does happen. Okay? So there's some exceptions to the octet rule, but Lewis theory is still very, very useful.